Welcome everyone to today's webinar on detection engineering, a modern approach for cybersecurity. In today's rapidly evolving threat landscape, the ability to identify, analyze, and respond to malicious activity is more important than ever. Detection engineering has emerged as a critical discipline in cybersecurity, allowing organizations to build resilient security detection systems. Detection engineering is not just about writing rules, it is a structured approach that involves understanding adversary behavior, designing effective detection logic, integrating detections into security operations workflows, and also continuously refining detection coverage. By leveraging tools such as CIEMs, EDR and XDR platforms, as well as threat intelligence sources, organizations can systematically craft, test, and optimize detections to identify both known and emerging threats. Before diving deeper into this topic, let's discuss the key benefits of detection engineering. One such advantage is improved threat detection, as it prioritizes behavior-based detection, allowing organizations to better identify real attacks. Also, by leveraging the MITRE ATT&CK framework, detection engineering ensures comprehensive coverage of real-world attack behaviors, enabling security teams to counter adversary tactics effectively. Another significant benefit is the reduction of false positives and alert fatigue, as high-fidelity detection mechanisms help minimize unnecessary alerts, improving operational efficiency and allowing analysts to focus on real threats rather than being overwhelmed by excessive noise. Additionally, detection engineering empowers threat hunting by providing high-value hunting use cases, enabling security teams to conduct proactive threat identification and uncover hidden threats. It also enhances log visibility by ensuring that organizations collect and analyze the right logs, filtering out unnecessary noise, and allowing security tools to function efficiently with the relevant and actionable data. Furthermore, by focusing on detecting tactics and procedures instead of just indicators of compromise, organizations force attackers to work significantly harder to evade detection by increasing the operational costs for adversaries. The most effective approach to creating and maintaining detections is by adhering to a structured and methodical process. The detection lifecycle is one such approach for developing, testing, deploying, and refining security detections. It ensures that security teams continuously improve their detection capabilities by iterating through a cycle of threat intelligence analysis, rule creation, validation, deployment, monitoring, and tuning. The 6 phases of the detection lifecycle are also shown on the slide that you can see right now. Discovery is the first step of this lifecycle, which involves gathering detection requirements. This phase can be initiated from multiple sources. Common sources include requests from security operations teams, maybe red team assessments, and also threat intelligence reports. Each of these contribute valuable insights into potential threats that require additional monitoring. This is followed by the research phase, which is essential for defining the detection logic that needs to be implemented and identifying the necessary telemetry required by said logic. If multiple detection requirements exist, this stage will also involve prioritizing them to ensure the most critical threats are addressed first. Building upon the insights gained from the research phase, the objective of the development phase is to implement the previously identified detection logic. This translates research findings into practical threat detection rules, moving from a theoretical understanding to operational capability. The testing process involves the use of 2 key data types: known good data, which helps prevent false positives by ensuring benign activities do not generate alerts, and also known bad data, which confirms that the detection effectively identifies malicious behavior. While both data types have their complexities, a general best practice is to ensure that known good data is sourced from an environment that mirrors the target environment as closely as it can, while known bad data is typically obtained through adversary emulation exercises. This phase may also incorporate unit testing within the continuous integration pipeline, which is used to check that certain requirements are met, like making sure that all necessary fields are included and the values are also correct. Okay, the second to last phase involves deploying the finalized detection rules into a production environment. This process is most effective when it is done through a detection as code pipeline that uses continuous development automation to make sure everything is deployed smoothly and in a controlled way. It is also important to ensure detections remain effective, accurate, and relevant over time. Threat actors continuously evolve their tactics, techniques, and procedures, aka TTPs. And if detections are not regularly updated, they may become rather outdated, leading to false negatives, also missed threats. Changes in the monitored environment can over time result in excessive false positives, which also necessitate detection rule tuning to prevent the alert fatigue of analysts. These tuning efforts constitute the final continuous tuning and improvement phase of the life cycle. Prioritization obviously plays a crucial role in detection engineering, especially during the discovery phase, by helping us address two key questions: what should be detected and how. On screen, you can see the pyramid of pain, which was created by an individual named David Bianco, and it visually describes the difficulty adversaries face when defenders focus their detection efforts on different types of threat indicators. The pyramid categorizes indicators from least to most difficult for attackers to alter. For instance, an attacker can quickly change the IP address used for command and control, but modifying or replacing the tool they use for this purpose would be significantly more challenging. By leveraging the pyramid of pain, organizations can shift detection efforts towards higher value indicators, specifically attacker TTPs, which are, as you can see, at the top of the pyramid, and they require attackers to expend considerable effort to change. The higher you move up the pyramid, the more strategic and effective your defenses become, the greater the operational burden you place on attackers, and the longer lasting your defensive measures become. The industry standard reference for attacker TTPs is the MITRE ATT&CK framework. If you don't know, ATT&CK stands for Adversarial Tactics, Techniques, and Common Knowledge, and it is the name given to a globally recognized knowledge base that documents real-world adversary TTPs used during cyber attacks. ATT&CK provides a structured way for security teams to understand, analyze, and defend against cyber threats. Tactics represent the high-level objectives that adversaries aim to achieve during an attack, and techniques describe specific methods for adversaries, or rather specific methods that adversaries use to achieve their objectives. The objectives in this scenario can be considered the tactics that we spoke about a moment ago. And then procedures describe how specific threat actors or malware use these techniques in real-world attacks. In general, we recommend creating an inventory of your organization's detection capabilities for each of these TTPs in the ATT&CK framework. For this purpose, you can use MITRE ATT&CK heat maps, which are a visual representation of an organization's detection coverage across these various TTPs that the MITRE ATT&CK framework contains. Heat maps help security teams prioritize detection engineering efforts by highlighting which techniques are likely to be already detected, what detection gaps exist within the environment, and which techniques are commonly used by adversaries that target the given organization. The created heat map will give you valuable insights into identifying and prioritizing attacker capabilities that you may be unable to detect with your current rule set. Okay, the objective of detection engineering is to develop efficient, scalable, and high-fidelity detections. To achieve this, it is essential to employ some key principles. You should prioritize inclusion by exception, which is a concept where allowed behavior is explicitly defined and anything out of that baseline is flagged. This is in contrast with exclusion by exception, which attempts to filter out known benign activity and often leads to a constant reactive tuning and also the growing complexity of the given rule. You should also utilize correlation strategically, but avoid creating overly broad rules that may introduce a sort of brittleness, and it might be sort of easy to evade such detection rules. As discussed with the pyramid of pain, focus on detecting behaviors rather than IOCs, unless IOC-based detection is the only viable approach. Also, you should ensure simplicity in the rules that you design, as overly complex rules can lead to more difficult to interpret alerts. Reducing false positives can sometimes take priority over eliminating false negatives, as excessive alerts can lead to analyst fatigue and decreased operational efficiency. Detection logic should be formatted to clearly reflect logical precedence and grouping for better readability and maintainability. Alert classification is the process of categorizing the security events that have or have not been generated by detection rules. True positives occur when a detection correctly identifies a malicious activity, allowing security teams to respond appropriately. False positives, on the other hand, are benign activities mistakenly flagged as threats, leading to unnecessary investigations and, in extreme cases, alert fatigue. This type is probably one of the most common to occur in security operation environments. And false positives are not necessarily a problem as long as they are properly managed and kept under control. True negatives represent legitimate activity that are correctly ignored, ensuring the system does not generate unnecessary alerts. And then finally, false negatives are the most dangerous, as they indicate missed malicious actions that bypass detection, leading the organization to be vulnerable. Striking the right balance between reducing false positives while minimizing false negatives is a key challenge in detection engineering, requiring continuous rule tuning. Striking the right balance between reducing false positives while minimizing false negatives is a key challenge, requiring continuous rule maintenance. Detection metrics serve as a quantifiable approach to evaluating the performance of security detections, helping organizations assess the efficiency, accuracy, and overall impact of the detection strategies. Let's discuss some of the most critical detection metrics. The false positive count metric represents the number of alerts that were classified as a false positive. A high number of this may indicate a noisy or overly broad detection rule, leading to increased false positives and potentially alert fatigue. Average time spent per detection measures the average time an analyst spends investigating alerts triggered by a specific detection. A high value suggests insufficient context, missing evidence, or poor alert documentation, and this forces analysts to spend more time investigating these alerts. Whereas a low value could indicate that analysts are not thoroughly reviewing the alerts, possibly leading to a potential oversight. Detection coverage evaluates how well an organization's detections map to real-world attack techniques and adversary behaviors. This is often visualized as the previously mentioned MITRE ATT&CK heat map, and this metric helps identify gaps in detection capabilities, ensuring the organization monitors key attack vectors. Low detection coverage score means that certain attack techniques are not effectively detected, leading to blind spots in the security posture. Storing detection crucial for ensuring scalability, automation, and maintainability in detection engineering. Detection logic should be stored in Sigma, an open source generic signature framework specifically designed for writing CM-agnostic detection rules in YAML. It allows security teams to create structured detection rules that can be converted into query formats specific to different CMs and log analysis platforms. Instead of writing separate queries for each tool, Sigma enables you to create rules in a standardized way and define detections that are highly portable and reusable. Public Sigma translators such as sigconverter.io or uncoder.io allow users to convert Sigma rules into platform-specific queries, enabling seamless integration across various security tools. By leveraging Sigma, organizations can improve detection consistency, enhance threat hunting, and simplify rule management across multiple security environments. Sigma is very useful for storing detection logic, but that's truly the only thing that it's very good for. A highly effective approach for storing additional metadata is using something called TOML files. TOML stands for Tom's Obvious Minimal Language. It is a lightweight human-readable configuration format designed for clarity, simplicity, and ease of use. It is widely adopted for configuration files across various programming environments due to its structured yet straightforward syntax. Compared to JSON and YAML, TOML offers improved readability while maintaining strong data structure support. TOML is also very script-friendly, which makes it a great option for automated processing in CI/CD pipelines. This helps ensure smooth integration and accurate validation of detections. Detection as code is a modern approach to developing, managing, and maintaining security detections using software engineering principles. You can think of it as one specific technical approach of implementing detection engineering principles. It treats detection rules and logic as structured code, enabling security teams to apply version control, automation, testing, and continuous integration practices to threat detection. By adopting detection as code, organizations can optimize workflows, reduce the manual effort required for deploying security use cases, and maintain consistent threat monitoring. Regarding version control and collaboration, we can use Git or a similar tool to track changes, which allows teams to collaborate on detection rules and maintain an audit trail of modifications. Automation and continuous improvement enables automated testing, validation, and deployment of detections, ensuring they are effective before production deployment. This approach also provides a standardized approach to managing detections across multiple security tools and environments, ensuring scalability and consistency. It also ensures detection rules are accurate, high fidelity, and optimized before deployment, reducing false positives and negatives. In other words, all detections going through this pipeline are properly tested and validated before being deployed. Okay, let's discuss an example of how a detection as code pipeline is structured. Detection rules are written in a structured format, such as TOML files. These rules are stored in, for example, GitLab, which serves as the central location for collaboration, review, and change tracking. When a new detection rule is added or an existing one is updated, the CI/CD pipeline automatically kicks off a validation process. This includes checking the syntax and validating the rule data using various Python scripts to make sure everything works as expected. Following successful validation, the pipeline proceeds to the deployment stage, and here the validated detection rules are automatically pushed to the target environment. This ensures that new or updated detections are seamlessly integrated into the organization's security monitoring infrastructure without requiring any manual intervention. Okay, as previously mentioned, we need to ensure that the given detection logic is sound before we deploy it into a production environment. We can use adversary emulation platforms to help automate this process. These tools simulate real-world cyber threats by replicating the TTPs of known threat actors. It is used to test an organization's detection capabilities, incident response readiness, and security controls. One such tool is Atomic Red Team, which is an open source adversary emulation framework developed by a company or team, I'm not too sure, maybe group, called Red Canary. And it provides a lightweight, easy to execute set of tests that simulate real attack techniques mapped to the MITRE ATT&CK framework. These tests allow security teams to safely validate detections, tune alerts, and improve defensive strategies without the complexity of full-scale red teaming. Perhaps also costs, that might be a consideration. Atomic Red Team is highly extensible, allowing users to easily create and customize their own atomic tests to simulate specific attack techniques. To create an atomic test, you must specify at least two very key components: a command that needs to be executed and also an executor that will run the command that you defined. This can be something like PowerShell or maybe Bash. Additionally, Atomic Red Team provides some other advanced features, including cleanup commands, prerequisite checks, and prerequisite retrieval to ensure these tests run smoothly in different environments. We'll also see a practical view of this during the demo section as well. Atomic tests are stored in a YAML format, which may not always be the most intuitive or user-friendly to work with. To address this, Atomic Gen was developed, providing a GUI-based approach. And if we want to see this in practice, I suggest we move on to the demo part of our presentation. For this, I'd like to ask the assistance of my colleague Gabor, who will take over the screen sharing duties, and we'll have a look at a specific scenario. So please, Gabor, go ahead and share your screen. Okay. Hopefully everything's working. I'm lagging a little bit on this screen, so hopefully I'm still, everyone can hear me and everything's all fine. So in our scenario, let's say we've received a detection requirement from our threat intelligence team regarding a lol bin that is not covered by our existing detection capabilities. Lol bins, if you're not familiar, are living off-the-land binaries, which are legitimate executables or scripts that come pre-installed with operating systems. Attackers can misuse these trusted tools to carry out malicious activities such as downloading payloads, executing code, or evading detection without relying on any custom-written malware. This technique helps them avoid detection capabilities and blend in with normal system operations. In our example, we will use a binary named vShadow. You can see this on the screen right now as well. This is or can be leveraged by adversaries to execute arbitrary programs. Okay, on the screen right now, we can see a specific description about how you can use this built-in system tool to execute, in this case, something called file.exe. So as previously mentioned, we don't have a detection method in place for this behavior, meaning that attackers could potentially use vShadow to launch arbitrary payloads without being noticed. So let's start building our detection capability for this. Firstly, we want to go ahead and simplify testing. And to do this, we'll create an Atomic Red Team test procedure. We'll be a tool called atomicgen.io. I think we mentioned this on the previous slide as well. And then we'll begin by filling out the necessary fields. So we'll start with the name. That should be pretty obvious. We'll give it a name that accurately describes what we're trying to do. Same thing goes for the description. We want to give something that will accurately describe what we're trying to do. And then under the supported platforms, we're going to select the platform that we are targeting. In this case, this is Windows. And then under the attack executor menu, we are going to set the interpreter that we're going to use to run our scenario. In this case, this is command prompt. Okay, under the command or the attack command field, we're going to add the payload we want to execute. In this case, we're not going to use the file.exe that we saw on the lolbats webpage. Instead, we're going to just use calc.exe, which is Windows's built-in calculator. And then this is pretty much all that we're going to be using for our scenario, but there are some additional fields that we're going to discuss. So that you can also define cleanup commands. These are coming from the name, commands that will be executed to clean up any artifacts that are left by our attack command. So one simple example for this would be if we maybe drop a file that we need for our scenario, we probably don't want to leave that on the device. So we probably want to have a simple command that will delete this file from the file system. And then also under dependencies, we can define prerequisites that are needed for the given scenario to be able to run. And then we can also define remediation steps to maybe download tools or any additional files that are a prerequisite. And this is all just to make sure that everything's in place before the scenario is executed. Okay, none of that is needed. So we have our fields now filled out, so we can copy the generated YAML into the appropriate technique file within the Atomic Red Team folder. Give that a second to go. Copy all that in, fantastic. Now let's execute the test and observe the resulting telemetry. Give this a second to run. And then we have our calculator that popped up. So we were able to use this lol bin to execute our malicious payload, in this case, calculator.exe. So Gabor's gone ahead and opened our Elastic instance that has the endpoint logs from the affected system connected. And this will give us insight into the relevant log data that we need to build our detection logic around. From our test results, we can see logs showing vshadow.exe being executed with the exec flag. And this is precisely the activity that we would like to detect. So to build our detection, let's open a Sigma template file and begin crafting our detection logic. So let's go ahead and start filling out our metadata fields. The title is what we'll be starting with. And yet again, we'll give it something descriptive that indicates what we're trying to do. Then under the UUID, or rather the ID field, we're going to generate a random GUID that uniquely identifies our rule. Next, the status field will indicate the maturity of our detection capability. Values that you would have here would be things like experimental, testing, or stable. Some other fields also could exist, for example, deprecated or unsupported. In our case, because we're creating a brand new detection capability, we're going to go with the experimental status. Again, description should be pretty self-explanatory. We're adding additional details about how our detection capability works. And then also we're going to add ourselves as the author. In this case, we are demo. And then in the reference section, we're going to add the relevant links for our detection capability. This is sort of for documentation purposes. So we're going to add the lolbas link that we were looking at earlier. Date will be today's date. So that's when we created this detection capability. That's all sorted. And then under the log source category, we're going to set up two specific fields. Category, this defines the types of logs we want to use. These types of logs could be things like file events or registry modifications. In this case, we will be using process creation logs. And then under the product field, we will define the system type for the log source. In this case, this is Windows. Okay, we're going to skip over the detection section for a moment and go straight to false positives, where we would put any non-false positives. In our case, because this rule is brand new, we obviously don't know of any yet because it hasn't been tested or seen in a production environment yet. On the level, we're going to set the severity of our alert. In this case, this is going to be medium. And then under the tags section, we're going to add the MITRE attack information. If you were maybe paying close attention during the lolbas page, you would have seen that the technique ID is 1202, which falls under the evasion tactic. Okay, now we can move on to the detection logic, which is going to be the meat and potatoes of our Sigma rule. The detection logic will consist of two main components: identifying the execution of vshadow.exe and then detecting the presence of the exec flag in the command line. Basic approach to detecting execution is by matching the executable name, in this case, obviously vshadow.exe, and Sigma uses sysmon field name, so we should use the image field for this. We will use the ends with modifier because the field that we are using will also include the whole path of vshadow.exe. However, adversaries might rename the binary. So to strengthen our detection, we can also match on the original file name attribute. But it is also important to note here that this field is only available when sysmon is configured on the relevant system. In Sigma, the dash symbol is used in a selection to convert the default AND relationship into an OR relationship. The other section we're going to create handles the command line condition. You can reference the command line data using the command line field, and here we will use the contains modifier, as our command line will contain other data as well. So we've got our exec flag set up there, all good. And then these two defined selections will be combined using a logical AND operator. Obviously, we want both conditions to be present. Once our detection logic is complete, the next step is to fill in the TOML rule file. Get that opened up. There we go. Let's start by completing the metadata section of this file real quick. Let Gabor get that done real quick. Okay, and then in the Sigma field, this field references the file name of the corresponding Sigma rule that we have just created a moment ago. So let's get that copied in as well. Cool. And then the atomic field specifies whether an atomic test is available for the rule. And of course there is, because we have created one at the beginning of our demo. Next, in the rule section, we can copy the values for fields such as author, description, name, false positives, and the rule ID from the Sigma rule we created earlier. Obviously, this is a little bit of redundancy, and there are some community initiatives that aim to resolve some of the redundancy we're going to see now and later on, but none of them are quite production ready yet. Get everything copied across. Gabor's hands are on fire. He's going as quickly as possible. All good. And then what we are going to do is, in addition to the severity field, we're going to define something called a risk score, which serves to classify alerts under a specific severity. In this case, a risk score between 22 and 47 is what corresponds to a medium. So Gabor has gone ahead and set us to 47. For the query field, we will translate the previously Sigma rule, in this case, into EQL or Elastic Query Language. For this, we're going to use a tool called sigconverter.io. Again, we mentioned this at the beginning of our demo. And let's get all of that information copied across. Cool. And then the threat section should be supplemented with the tactic technique ID and name, in addition to the details already present in the Sigma rule. So we're adding a little bit of additional detail, as the Sigma rule we created earlier does not explicitly contain tactic information. Obviously, it does implicitly from the technique ID. Give Gabor a second to get all our information copied across. And then we're missing our name. Yeah, system binary proxy execution. That's the name of T1202. Okay, the final pieces that need to be added are the investigation fields, note, and alert suppression fields. The investigation field setting defines which data points will appear in the initial alert view. These usually include a mix of elements from the detection query and additional context, such as things like the host name, and these all support quick triage activities. Okay, in the note field, we will add an investigation guide, which is intended to assist in triaging alerts generated by this detection rule. And then finally, in the alert suppression field, we can prevent duplicate alerts from being generated from a single rule execution based on one specific or multiple specific fields. In this case, we will use host.name for suppression. And then basically we're done. And then to close out the detection gap that we had observed at the beginning of our demo, we will open a git bash terminal and push the new rule file to our detection repository. Let's get that copied across, add it to Git, get it committed, very detailed description, and then let's push that to the repo, give it a second to run. There we go, it's pushed. And then let's also rerun our atomic test. Same one that we created at the beginning, and then we have our calculator.exe launched again. And then, if all has gone well, we will open our repository in GitLab, and it is still being executed. But as I see, okay, we are now done, and the validation and deployment stages of our pipeline have completed successfully. This means that if we open Elastic and then go to the rules page, we should be able to see the V-shadow detection that we just created. There we go. And that also means that on the alert page, we should be able to see the alert created by the detection that we have just created. Hopefully, there we go. Oh, no. Give that a moment. Seems like our query didn't run in time. Let's see if manually running it will give us the information we want to see. There we go. So those two would have created alerts within our environment. So basically, we're now done. This detection gap that was identified by our threat intelligence team has been filled in a way that is maintainable and scalable in the future. Okay, we've now reached the end of our detection as code demo and also our webinar. We have discussed the ethos of detection engineering and have seen a practical example of how detection engineering can be used in the real world. This is the exact methodology we use in our SOC, our Security Operations Center, as well, to ensure our customers have resilient and up-to-date detection capabilities through a platform-agnostic approach. By now, you hopefully have a good theoretical understanding of how detection engineering works. However, you may have observed that some of the tooling and custom developed software required to implement detection as code, specifically with specific CM systems, we didn't really cover that in depth. This is because creating these tools is more of a software engineering question rather than something specifically related to cybersecurity. As such, I think it's maybe a little bit less interesting. But if you thought that, I have good news for you, because the tools used in our demo and in our production environments will be released in an open source repository as a dedicated community fork of our internal tool set. This will be released in the near future, so we're working on this community fork as we're speaking. So make sure to follow us on our socials to make sure you are notified when these tools are released. Okay, if you have any further questions regarding detection engineering or any other services that we provide, feel free to send us in an email or contact your account executive if you're an existing customer. Also, we have an exit form, or rather a questionnaire, that we'd be very grateful if you filled out. Please, someone drop that in the chat so everyone can grab that, and please fill it out if you have the time. And I'd like to wholeheartedly thank everyone for joining our webinar, and I wish you a pleasant rest of your day. Thank you very much.